A heating curve is a graph that shows how temperature changes as heat is added to an object. So the vertical or y-axis of our graph is temperature, maybe in degrees Celsius. The horizontal or x-axis is heat added, or Q, and the units of that will be joules. Here's an example of a generic heating curve. So, the substance is all solid in this region right here, it's all liquid in this region, and it's all gaseous in this region. The horizontal regions, here and here, represent phase changes. Right here on our graph, we are melting. If we're going the opposite way, we are freezing. Melting requires putting heat in. Freezing requires taking heat out. But notice the temperature is constant during those phase changes. Up here, going to the right, we start out 100% liquid. We end up 100% gas. That's vaporization. On the other hand, going the other way is condensation. Note that the amount of energy necessary to vaporize is greater than the amount of energy necessary to melt. This is always the case because a gas is so much higher than a liquid on the potential energy scale. Remember this diagram? We have solid down here, liquid just above it, and gas is way up here. Right? So this distance here is proportional to this distance. Whereas this distance between solid and liquid is proportional to that distance. The distance between 100% solid and 100% liquid on the phase diagram. Sorry, this is not a phase diagram, this is a heating curve. What are you talking about? So, these flat regions, these phase changes, where temperature doesn't change, we can record our observation delta T of phase change equals 0. This means that phase change is a change in potential energy. Whereas, when you're on the sloped portions, your temperature is changing as the heat is added. This is because temperature is proportional to the average kinetic energy of the particles. Starting here, I'm very cold. I'm a solid. As I add heat, my temperature increases until I reach the melting point. Right here, the melting point. And then all the heat that I add goes into melting the substance. Right here, it's like having a glass with ice cubes in it. Right here, you've got a glass of ice-cold water, but all the ice is melted. When I get onto the next sloped portion, here, now I'm water that's getting warmer and warmer as heat is added. And now it's approaching 100 degrees, which is the boiling temperature, or the boiling point. And once I've reached the boiling point, then when I keep adding heat, the heat goes into boiling the liquid. Right here on my line, half of my liquid has boiled away to become steam. By the time I get here, all of my liquid is gone and it's 100% steam, but it's still at the boiling temperature. Now here, the temperature of the steam increases as heat is added. Now, we can think of heat as being a form of energy known as enthalpy. And the symbol for enthalpy is delta H. And so Q and delta H are related. There's two different equations for Q, depending on whether you're in a flat portion of the heating curve or a sloped portion. If you're in a flat portion of the heating curve, you need to use Q equals N delta H for whatever phase change you have, where N is the number of moles of substance, and delta H is the molar enthalpy of phase change. For instance, for water, the molar enthalpy of phase change, delta H vap, for going from a liquid to a gas, is 44.0 kilojoules per mole. So if you had 1 mole of water, it would take you 44 kilojoules to vaporize it. On the sloped portions, however, you use a different equation, Q equals M CS delta T, where M is the mass of substance that you have, CS is something called the specific heat, and delta T is the change in temperature. It's the final temperature, TF, minus the initial temperature, TI. Specific heat is the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. The specific heat of liquid water is 4.184 joules over grams times degrees. And that degrees can be degrees Celsius or it can be kelvins, and it doesn't make a difference. Because a delta T is the same whether it's Celsius or kelvins. Here's an exercise. How much heat is needed to warm 100 grams of water from 25 degrees to 98 degrees? Use the equation with Q equals MCS delta T. Go ahead and pause your video while you work it out. So first thing we should do is make sense of all the information that we were given. 100 grams, that's clearly the mass. 25 degrees Celsius, that's the initial temperature. 98 degrees Celsius is the final temperature. Now, the equation we're going to use is Q equals M CS delta T. We have M, and we know the value of CS, it's 4.184 joules over grams times degrees C. Delta T, we're going to get by taking the final temperature, which we know, minus the initial temperature, which we also know. So we get a delta T of 98 minus 25 equals 73. Double check my math because you know I'm terrible at it. But assuming we've done that correctly, we have Q equals 100.0 grams, that's M, times 4.184 joules over grams times degrees Celsius, that's CS, times delta T, which is 73.0 degrees Celsius. And as you can see, grams cancels and degrees Celsius cancels, and we get an answer in joules because heat is a form of energy. And my calculator tells me 3.05 times 10 to the 4th joules of energy. Should be a lowercase j. This is a perfect time to define heat as opposed to temperature. Heat is the energy transferred from an object at higher temperature to an object at lower temperature when they are in contact. If you have a larger object, like an iceberg, that actually contains more heat than a cup of steaming hot espresso, simply because there is so much more iceberg than there is coffee. And I mean, let's face it, if you had an iceberg's worth of espresso, you'd be pretty shaky at the end of the day. So let's say I have two objects, A and B, and A is hot and B is cold, and I put them in contact. Well, heat is going to flow from object A to object B. And we can say that QA equals negative QB. This is just saying that the same amount of heat flowed out of object A as flowed into object B. And generally, when heat's flowing out of something, we call it negative. So it would be just as good to say QA equals negative QB.